So first I'd like to introduce Emli-Mari now, Dr. Emli-Mari now. Emily started off at the University of Stellenbosch, completing her undergraduate and PhD in electrical and electronic engineering, specializing in digital signal processing. She then began her career in research at the Vicon Research Institute in Oxford, followed by her postdoctoral work with David Mackay's research group at the University of Cambridge. She's now the head of research at Impaired Capital, looking into Bayesian research on automatic trading and organizing machine learning summer schools in her spare time. Please give Emily a warm welcome.
So, thank you very much for the opportunity to present this formally. So I would also like this opportunity to dedicate this talk to the late David Mackay. He did pioneering work in the fields of assistive technology, Bayesian inference, machine learning, information theory, and sustainable energy. And he was knighted just before he died for his work on sustainable energy. So Ticker was a collaboration with him and the last assistive technology program that he worked on. So I thought it would be nice to dedicate it to him. So he wrote 2 books. The first book is on information theory and learning, and the second on sustainable energy. Both books are available to download for free on his website. And there's also a video lectures course available that you can watch that's also free, that goes with the information theory book. So a lot of the foundational work in this presentation comes from that book. So to talk about Ticker, which is the assistive technology program I'll be talking about, I would like to start with the origins, which is Dasher. So it all started with David's Nature paper in 2002. He developed this program with his group, and a series of papers followed from there. It is really a groundbreaking piece of software for people who have motor impairments. So you have to think of driving. You drive with your steering wheel and you point into a direction. All letters are sorted in alphabetical order, and the size of each letter, of the box for each letter, is proportional to the probability of the letter given what was written before that. So after you've selected the first T, all subsequent sentences following that T will have T as the first letter of the book you are writing. I will give you an example to start off with. Here, a very rudimentary, noisy head tracker is used to write using Dasher. As you can see, it is alphabetical, but once you've selected T, H is the next probable letter. And this, here we are trying to write, this is fun. So here you can see the pointer is very noisy, but due to the strong dependence on a good language model, you can write fairly quickly with this noisy input device. So you can also write with a mouse, and I will show an example of a breath sensor that you can also use to write with. So with a mouse, you can write up to 30 words per minute. More frequently used sentences are easier to access. Sentences are represented by binary codes, and sentences with higher probabilities result in shorter codes, so they are more compressible. So better language models result in shorter codes and faster text entry rates with high accuracies. So this is an example of a breath sensor, and David was the expert here, and he could write up to 16 words per minute. So you can imagine that recent advances in NLP can have a huge benefit for Dasher. It is estimated up to a factor 2 in speed. And this is huge considering that the average keyboard typist enters text at 40 words per minute. Nomon and Ticker, that I will discuss in a minute, are similarly dependent on good language models. An appropriate training text corpus is also, of course, beneficial. So in this case, typical sentences used by people in the accessibility community. So way back during my time at Cambridge, we were approached by the fMRI group at the university, and they were looking for a text entry method that can go from a brain scan to a piece of text. The user is asked to think of an activity such as tennis, and when the corresponding part in the brain is activated, a button press event is emitted. So this is quite an extreme application because these users are in fact unconscious. But to think a little bit about what do we need. In the first place, the breath mouth is continuous. We need a binary signal, a 1 or a 0, when the button press is active or inactive, and we need a program that is extremely noise tolerant. So at the time, a single button version of Dasher did exist, but it was simply not noise tolerant enough. Once you are also in a box, it is very difficult and expensive to reverse. So what you're really looking for is a program that can also maintain the probabilities of all the possible sentences of words that could have happened in the first place. And despite these shortcomings, Dasher also has the problem that it is a visual interface and we need an audio-only interface. So other examples of single switches include a hardware button, something like an EMG switch that can capture muscle motions. The breath mouse can be converted into a binary signal, and of course there's the brain scan. So our paths diverged a little bit from the fMRI group in the sense that we decided to focus on conscious people. So we focused on the user group with locked-in syndrome. A locked-in syndrome user is paralyzed. The lower part of the brain is destroyed, but the cognitive abilities are intact. This is typically due to a stroke or something like multiple sclerosis. The user is not in a vegetative state, and they typically have voluntary eye motions, but it is combined with involuntary motions, making the signal very noisy. And the hearing capabilities of these users are understudied, but empirically it seems as if most of them can hear quite well. So a switch event will typically correspond to an upwards eye motions, and this will be our button press. And a series of button presses have to convert it into binary codes that represent words, and Ticker does this conversion. So this is a typical user. She is confined to a wheelchair and she is paralyzed, and she can only use her eyes to communicate. So the gesture switch algorithm in itself is quite sophisticated. So this algorithm was also developed in-house, but I will just talk very briefly about it so that you can get an idea of the scenario. So there will be a training phase involved, and in this case, the user makes whatever gesture she can do 3 times. And here she's looking up, and you can see that there is quite a bit of involuntary eye motions involved. Similarly, this user also has locked-in syndrome. He can do a little bit more. He can also move his eyebrows, and he can laugh. So, and then the machine learning algorithm has this semi-unsupervised learning phase, after which the gesture is automatically detected. And if the algorithm is sophisticated, it can output the distribution of the click times that you can expect with respect to some reference in time. So there are 2 distributions that are important. The first is the one associated with the noisy switch, and the second is the distribution associated with how the user interacts with the program they communicate with. So typical programs include the traditional scanning system, Nomon, and then the one we'll talk about is Ticker. So a probabilistic text entry method can infer a distribution for the click timing range. Likewise, the gesture switch algorithm that's probabilistic can infer, can give you some idea of the click timing range associated with the certainty that the event was in fact spurious. But most of the time, we have an algorithm that's not a sophisticated algorithm. It just gives you a delta distribution saying a yes or a no definitely not did occur, and it's typically not accompanied by a probability that the event is spurious. So it becomes the problem of the text entry method to infer the combined distribution of the switch and the user interaction. So a probabilistic text entry method can infer this distribution, and you can also imagine that we can now draw samples from this distribution in order to simulate the performance of the text entry method. And that was one of the techniques we've done to evaluate it. You can also imagine that things can become quite interesting now. You can use this distribution as input to another machine algorithm to detect and exploit underlying latent dependencies between disabilities. So to give you an idea of a traditional scanning system, this is the type of program that's mostly used in practice. A person selects a letter or a word by going through a row and column scan. So first you select a row and then a column. So to select H, you'll go through 2 row scans, select row 2, and then scan up to H, which is 6 scans in total. This program is not probabilistic to begin with, but we have written a paper that's on arXiv to convert it into its probabilistic version so that we can compare it with the probabilistic text entry methods. It does not take the distribution as part of the interface into account. And to cope with false positives, it just uses error corrections. So it can become very cumbersome if your switch generates false positives. To cope with long reaction delays, the scanning delay is simply increased. So even for a modest disability, it can become quite tiresome. So if the scanning delay is 1 second, your average text entry rate would be about 2 words per minute. But when you increase it to 5 seconds, which is not outrageous for a disability, your text entry rate will reduce to less than half a word per minute. And this is just considering the average. We haven't even looked at the standard deviation of your click time distribution or false positives. It just becomes worse. So a program that was developed in David McKay's group by Tamara Broderick is called Nomon. I'm not going to talk a lot about this. I'm just mentioning it because it's a visual interface and we're going to focus on audio only. But it basically has a large number of selections. All the letter clocks occur always at the same position, but then there are certain word predictions as well, allowing you to select a word with just a few clicks. And there is a statistical distribution driving this. But you do select 1 letter at a time. So it is a bit sensitive to the user's latency response, but it allows you to compensate for much more noise than compared to the traditional scanning methods. So Ticker is an audio-only interface. It is actually very simple. You read the alphabet R times in a pseudo-random sequence. And you click whenever you hear the letter that you want to write. After R repetitions of the alphabet, you update the posterior probabilities of all the words in a predefined dictionary. And the prior year would be determined by your language model. You can also have quite a sophisticated character model. But if that probability is above a certain threshold, you select your word. In spirit, it is very similar to the T9 mobile interface. So because we have a model and we defer that latency up to the end of the word, it allows us to play sounds in rapid succession. You never stop. And this is a huge benefit at the point where a latency problem or a noise problem in terms of standard deviation becomes problematic. So there is a paper that will come out in the year, a journal paper. The appendix of the paper is on arXiv, and there's also some software on GitHub if anyone is interested. So to give you an example, here is a pseudo-random sequence where the alphabet is read twice to the user. When you want to select the letter B, for example, you click when you hear that letter. And what we have to do is we have to compare the received click time vector T with all possible click times in the range big T, which represents all repetitions of the alphabet. So we have to compare the probability of T given a letter L and all our parameters. So the parameters is typically an ensemble of parameters. To go a bit further into that example, we have the same sequence, and here this is the model for one click. You can potentially click twice, but say you click only once. We have a false positive model. This is done via a Poisson process. The false negatives are modeled with a fixed probability, and here the alphabet is read in 5.2 seconds, which is quite fast for an audio program. And we assume Gaussians now at this stage for true clicks. And if the model is not misspecified, the mode of the Gaussian will occur at the typical point where associated with a B. So here you can also see there's a non-zero floor rate, so that's effectively a heavy tail that is there because of the false positive model. So that's quite a nice way to include a probability that anything unexpected can happen with some small probability. So the alphabet sequence is in fact the result of an optimization process, and for ticker it is fixed because later on we will start using stereophonic sounds and then the cognitive load becomes too much if it's not fixed. So the user knows when to expect what letter. But important to notice is that letters that occur close in time to the letter B during the first repetition typically occur far from it during the second repetition. So X occurs just before B during the first repetition, but during the second repetition, it's separated with about 5 letters. And this concept of distance should actually be visualized in 2 dimensions. So at the bottom, the means of the Gaussians before are now shown. So at the, on the x-axis are the means of these are the means of the first repetition. So here you can see that there's X and there's B just next to it. But during the second repetition, they are separated with a few letters. So now you can get the idea that no 2 letters occur close to each other in 2D. So that second click helps you to disambiguate. So when you have more noise, like with the unconscious patient, you can just add more repetitions of the alphabet, and you can start to shuffle these things. So the idea is very simple, but it is quite powerful. And here you can see, because the standard deviation is quite low, we end up with a sphere in 2D. So it will be very difficult if you click twice and your model is right. It will be easy to disambiguate between a B and all other letters. And this is not even taking advantage of your language model, which really make it a bit more easier to do the inference. So there is a binary code interpretation of the letters. If someone is interested in this, please talk to me afterwards, as well as for the words. And this is just to give you a flavor of how the click timing model for a specific letter looks like. There are some terms involved due to the false positives, and it is a mixture model. It's the result of some Bayesian inference algorithm. But most importantly, we currently assume Gaussians for the true click time distributions, but in the real world, it is not Gaussian in this scenario. It can be bimodal, for example. After the user used the program for a little while, they might get tired, so the mode might start to shift. It can be asymmetrical. It can have more than 2 modes. For certain letters, maybe the user can't hear certain letters well. We therefore use kernel density estimation combined with online learning. It's similar in spirit to Nomon, but there are more latent variables. So there is a bit more, the inference part is a bit more involved. There is an expectation maximization step. But important to note here, the training data you use are the words that the user have previously written. And there is also a calibration phase to start off in the right ballpark. So the gist of it is that you replace your Gaussian with something like this, and it can change according to the user's capabilities. So due to our modeling capabilities, we can place sounds in rapid succession, but Nomon is really able to parallelize the selection process due to all the clocks. We want to do something similar. So what we've done was to make use of stereophonic sounds combined with the cocktail party effect, relying on the ability of humans to filter out a chosen signal from a range of simultaneous auditory stimuli. So we assume the user wears headphones, and we now have exactly the same sequence as before. It goes F, Q, W, A, G, L, but there's one voice who will read the letters A to E in your left ear. And likewise, there would be another user reading the last part of the alphabet in your right ear, and the other ones are in between. So now, what will happen is your brain will typically filter out these things, and it will allow you to focus just on these letters, and they will sound quite slow when you're able to focus on them. So you can, in theory, get a factor 5 increase in speed if you use this. So this was this user's first reaction when he heard the program. So brace yourselves. I will play you a video clip now of one of the initial versions of the program. So this user took part in our user trial, and we first wanted to see if people can actually select sounds from 5 simultaneous audio channels, because we could only find papers where people could use 3 channels. And this was nothing like this. People didn't communicate using 5 channels or 3 channels. So this was an interesting experiment, and this user preferred method of communication was with a human involved. So he looked at certain parts on that board, and then the human would guess what he would like to say. And the scanning system didn't work for him. So just after a few user trials, this user could select letters from ticker at a speed of 2 words per minute with an accuracy of 80%. So I'm just going to skip a bit, but this is how it's...
Next, D left. Q, R, S, Y, T, Z, U, space, stop, R, S, T, U, Z, space, stop. Next, space, right. Q, R, S, Y, T, Z, U, space, stop, R, S, T, U, Z, space, stop.
You have written Brian.
New word, stop right. Q, R.
Yes, he's quite happy. So in the paper we have some results, and we've done quite a big user study where we've shown that users can, in fact, this was tested on able-bodied users, but quite a lot of them, and they were all able to select letters from ticker in 5-channel mode. So it's definitely possible. We first had to show this, and we also did this user study with the user with a motor impairment. And the second set of results shows that via simulation and with some user input, that the ticker and the standard scanning system like the Grid 2 are similar when there's no noise involved, but as soon as you inject some noise into the system, ticker outperforms the Grid 2 with quite a large margin. So here where the text entry rate of the Grid 2, it really does drop to a small number with just a bit of noise. So current research is still ongoing. Currently it's in the form of the Nomon project. Here Tamara Broderick is taking the lead. She's currently professor at MIT, and she's an expert in machine learning. A student, Nick is revamping Nomon, and Keith is also involved. He's at the University of Michigan, and he's an expert on language processing and speech recognition. And we're also working with an Oxford-based charity who helped us during my time at Cambridge, and they're involved again. So they're going to help us to collect and analyze click timing data from real users, and also compare Nomon to to existing software. So we've got ethical permission to conduct quite a big user study. So if anybody is interested to collaborate, please feel free to contact us. And there is also now an active project on GitHub where anybody can contribute and try out the software. So thank you. Please feel free to ask questions.
Hi. That was very, very interesting. Thank you.
Thank you.
So my question was, especially when the simultaneous letters were being presented, like that was quite overwhelming just to like watch the person being subjected to that.
Yeah.
And my question was like, so it has the speed, you know, the throughput goes up when you use a technique like that. But do people get tired? And maybe do they get tired more quickly when they have to do more concentration to get the throughput higher? In that it's so maybe it works out that in the long run it's not worth doing that if people get exhausted more quickly.
It is quite interesting. Initially, it took a few sessions to get this person to start, but it's you actually have to try it on. If you have the headphones on, it is a completely different feeling. But this video is just to show what's actually going on. So you get used to it fairly quickly because you know the sequence of the alphabet. It's just as if you sort of get into the swing of it, and people actually enjoy using that, especially if there are false positives. People get less tired because I think with the scanning system, it actually makes them really tired to wait, you know, for 5 seconds before they can move on. So initially, yes, but after you've used it for a while, I would say no. So thanks.